So today I'm going to cover a background of kinetics and show an example from rate law. I got most of my stuff from the Edpuzzle about this, and then I looked over the PowerPoint, but it pretty much seemed the same, so I just used most of the stuff from there. But basically for kinetics, there's little particles around us that are always like bumping into each other and just moving about at different speeds, and when they collide hard enough, they can make a chemical reaction occur. And the power to do that is called activation energy. So I have that definition right here. It says the energy threshold that must be overcome to produce a chemical reaction. So I know in the video they use like the visualization of it having to go up over a hill, like having to gain enough kinetic energy to pass that threshold at the top of the hill to then form a chemical reaction instead of just not bumping into each other hard enough and bouncing back off. But over here I have that kinetic energy is the speed of those particles. So they're bouncing off each other and building energy, more energy, more energy. And then finally, once they've just gained enough from just bumping into each other, they've gained enough kinetic energy to make it up over that hill. And then down here we have the reaction rate, which is the rate at which the concentrations of the reactants decrease. And the reaction rate is like the speed of the reaction happening. And then over here is the rate law, the mathematical relationship between the concentrations of the reactants and the rate of a reaction. And the rate law is the equation that we're going to be breaking down, so it can be explained by this formula right here. This is the one that I got from the Edpuzzle video. I noticed that in the PowerPoint, instead of the N's and M's, they had X and Y, but that was basically the only difference. But for this equation, it's rate equals this K, which is the constant, and then A and B are whatever reactants you're working with. You're going to fill those in for those. And then N and M are the exponents that we're going to figure out later in this thing. So this is the chemical equation down here that we're going to be using. Sorry, I got to scroll over a little bit, but this is the first part, and then yields this over here. And then, so since we know what we're using there, we can go ahead and fill in our little equation here. So rate equals K, the constant, and then we're doing NO, I think it's nitrous oxide, and then we'll figure out the exponent for that on N. And the second one we're using is this H2 right here. So H2. And then to find these exponents, we have to perform an experiment. So right here I wrote down trial 1, we use the same X for the set amount of nitrous oxide and H2, they both have the same amount. And for that one, we got our rate in moles per liter per second was 0.006. And then to try to find a change to get that exponent for trial 2, we used the same amount of nitrous oxide and then doubled the amount of hydrogen, and that gave us exactly double this rate. So that means, sorry, I'm looking at my notes. So since we doubled the hydrogen and it doubled our entire rate, that means that the amount of hydrogen is equal to the it's equal to the rate. And that is how, that's how we're going to change this exponent. So we know that when hydrogen is 1, then our rate is going to change, or when hydrogen is 2, our rate is going to change by 2. When hydrogen is 3, our rate is going to change by 3. So just to make it equal to the rate, we're just going to make this exponent 1. And then for trial 3 down here, we use the same set amount For hydrogen, we put it back as x. But then for nitrous oxide, we doubled it. And then over here, we got 8 times the original rate. So that means that the exponent needs to be 3. So from here, let me change our exponent to 3. And then since we have both our exponents filled out for our equation, now we can figure out which order it is. So I wrote down a couple of the orders here. So 0 order, the reaction rate is constant and cannot be determined from the concentration, so we can't really use how we just use it to figure it out. It's just something on its own. For first order, the rate is equal to the concentrations of one of the reactants, so that would be, I guess that wouldn't be like that, never mind, sorry. And then for second order, the rate is equal to the concentration of one of the reactants squared, or the product of 2 of the reactants' concentrations. So to actually get your reaction, you need to add the exponents. So this reaction is a 4th order, which is actually kind of uncommon. And since, yes, our exponents were 3 and 1, you just add 3 plus 1 equals 4. That's your order. And that's kind of the simple math on how to do that. But yeah, I hope this explains rate law a little better.